All right, now let's look at the so-called Newton's second law, the most important of the Newton's three laws. So Newton's first law says you don't need a force to maintain motion, okay? Because motion maintains itself due to the inertia. So now the natural question is, so you don't need a force to maintain motion, so what do you need to use a force for, okay? Once you do apply a force to an object, what's going to happen? Well, common sense tells us that if you exert a force, a net force on an object, then it's going to start to, well, does it start to move? Well, if it's already at rest, it could start moving, which means its velocity has changed from whatever value, from zero value to whatever final value. Or if it's already in motion, using a force, you can slow it down, speed it up, even stop it, or you can make a turn. In any case, when you apply a force on an object, you are not just maintaining motion. You are actually changing its status of motion. In other words, you are changing its velocity. Okay, now different forces acting on different objects will have different effect in terms of changing its velocity. If you look at a small object without much mass, okay, and apply a lot of force, right, then what's going to happen? Well, obviously, its velocity is going to change very quickly, right? Like this pen again. Okay, it doesn't have much mass. If I push it hard, it's going to accelerate very quickly. Okay, it's going to pick up from zero speed, immediately reach a very, very large speed. So you're going to get a large rate of change of velocity. Velocity changes very quickly. You know the rate of change of velocity is otherwise known as what? Acceleration, right? So it is clear that the acceleration requires a force. That's what the force is for. You don't need a force to maintain velocity, but you do need a force to get an acceleration, which means to change the status of motion. And how much acceleration do you get? The acceleration that we get is proportional to the force. Does that make sense? Well, that is part of Newton's second law. We certainly have seen plenty of examples in real life. If you push something harder with a greater force, it's going to accelerate more swiftly. Okay, so A is proportional to F, but the same force exerted on different masses have different results, right? If you take the same force, you apply it to a much smaller, a much more massive object, it's not going to accelerate nearly as much, right? So the greater the mass, the less acceleration you're going to get. So it is also, it also makes sense to say A is inversely proportional to the mass. Okay, so the acceleration that an object experiences is linearly proportional to the force exerted on it, but it's inversely proportional to the mass. And what about the direction? Well, it makes sense that if you pull it this way, it's going to accelerate in this direction. Okay, so these are actually, A and F are in the same direction. So we conclude that A is proportional to the vector force over the mass. Now the constant of proportionality, I can arbitrarily define it as 1 unit. All I have to do is define the unit of force such that when A equals 1 unit value, M equals 1 unit value, F is also equal to 1 unit value. And that unit value for force in SI system is called Newton. Of course, we named it after the great Sir Isaac Newton. In fact, that's a common practice that we use throughout physics. That is, when we get a very commonly used important physical quantity, such as, for example, force. The SI units of this force, of this quantity, if I write down fully, will be a combination. Okay, in fact, if I write F equals ma, then the SI units of force would be that of mass times that of acceleration. That would be kilograms meters per second squared, right? That is the SI unit of force. But that's a combination. It's cumbersome to write. So what we do is we define it as 1 Newton. Newton, or just capital N, is defined as 1 kilogram meters per second squared. And that definition serves two purposes. First of all, it serves as a shorthand for kilogram meters per second squared. And secondly, it serves to commemorate the great physicist who taught us so much. So we have F equals ma, and that, of course, is a vector equation. And that is too small. I want to write it really large. F equals ma. Now, why do I make it that large? It is the most important equation in physics 1A, in classical mechanics. And many physicists will agree it is actually also the most important law in all of physics, not just 1A. Because, you know, when we study different aspects of the physical world, such as, you know, electricity, magnetism, optics, nuclear physics, atomic physics, molecular physics, all these things in different areas of physics, we're actually dealing with different type of interactions. Okay, for example, in electromagnetism, we study in physics 1C, we'll be dealing with electromagnetic force. And then later on, we're going to study, in modern physics, we study molecular forces, atomic forces, even nuclear forces. Those are different types of forces. But Newton's second law tells you, once you get a force, say electrical force, magnetic force, whatever, it tells you what this force is capable of doing. It is capable of producing an acceleration. Okay, so in different areas of physics, we're just dealing with different types of forces. But what do these forces do? Well, they do the same thing. They cause acceleration on an object. So that is why we're going to apply Newton's second law throughout entire physics, not just physics 1A. So, let us take a closer look at Newton's second law. As a first example of application of Newton's first law, let's look at a very special force, which is the weight. You know, by definition, what's a free fall? You drop an object, it falls down, up or down, in the absence of air friction. Okay, so we can basically, you know, imagine a case we can ignore air friction. An object will be moving under the influence of gravitational force of the Earth alone, which is the weight of the object alone, and then we say it's a free fall. Now, in a free fall, we know the acceleration has only one value. That's g going down, right? G going down. So A is equal to g. And there is only one force as well, and that's the weight, Fg, F sub g. G means gravitational. Now, let us apply Newton's second law to the motion of this object. Let us try to understand from a dynamical point of view what is causing this thing to do a free fall. Well, Newton's second law says F equals ma. Right? F equals ma. In our case, what's F? Well, it's the downward weight, Fg. Right? M is m, the mass. What about A? A equals g. So you see, we apply Newton's second law to the free fall of any object, and we found this important relationship, and that is the weight of an object equals its mass times the acceleration of gravity. That is a consequence of Newton's law, Newton's second law. And this is a unique force, by the way. And also, let's realize we're looking at a very special case. This is not just any force. This is a force that is always proportional to the mass. Okay? No other force is always automatically proportional to mass, but the gravitational force is, or the weight is. This explains why any object, regardless of the mass, will fall at exactly the same rate. Because if you double the mass, you would also double the force automatically. Force of gravity is proportional to the mass. So if F equals ma, mass doubles, force also doubles, the acceleration is left unchanged. That is a unique feature of gravity. It does not only apply to free fall, it applies to any case when the motion of an object is powered by gravity, such as a ball rolling down an incline, that is of course powered by gravity. It turns out the acceleration of the ball is also independent of its mass. You double the mass, you find it rolls down just as fast. We'll get to see many examples of that. Before we get to further applications of Newton's law, trust me, the examples of that, in fact, this entire chapter pretty much, the exercise problems are devoted to the applications of Newton's second law. Let us look at the remaining law of Newton in classical mechanics, and that is Newton's third law. Let's look at Newton's third law. What does it say? Well, in Newton's third law, there are two objects. Object 1 and 2. Actually, it doesn't have to be two separate objects. It could be two parts of the same object, whatever. This object exerts a force. Object 1 exerts a force on object 2. We call it F1 to 2. Okay? what does Newton's third law say? Newton's third law says that when object 1 exerts a force on object 2, which is F12, then Newton's third law demands that another force would be exerted by object 2 on object 1. And that force, of course, is called F21. The force exerted by 2 to 1. Newton's third law says this force, F21, has the same magnitude as F12. Okay? The only difference is that these two forces differ by an opposite sign. So, here's what Newton's third law says. If object 1 exerts a force on object 2, then object 2 simultaneously exerts a backward force on object 1, which has the same magnitude as the original force from 1 to 2, but it has the opposite direction. We call this pair of forces a pair of action and reaction. So the third law essentially says an action is always accompanied by a reaction. These two have the same magnitude but opposite direction, and they appear and disappear simultaneously. That is what Newton's third law says. As a matter of fact, if you apply Newton's third law, you think about it, you will get interesting consequences if you apply both the third law and the second law to study the motion of an object. Let's look at this example. Okay, this is the famous horse and wagon puzzle. You know, the horse pulls on a wagon, and if it pulls hard enough, the wagon moves, right? And everybody understands that. Now, we know from Newton's third law that if the horse pulls the wagon with a certain force, then the wagon also pulls the horse with the same amount of force backwards, right? So, here's the question. From Newton's third law point of view, these two, the wagon and the horse, exert the same amount of force to each other, except the horse want the thing to go forward, the wagon, given a force, want to pull the horse backwards. So the question is, how come the horse always wins? Okay, that's the question. How come it always wins, despite Newton's third law, which says that the push and pulling force are actually equal to each other? That is the puzzle. To understand this puzzle, we have to have a better understanding what F equals ma truly means. What is F? What is m? What is a? M, of course, is the mass, and a is the acceleration. But when you say F, the force, what are we talking about? Are we including all the forces that you draw? Well, let us be very careful about it. First of all, when we apply F equals ma, we have to first identify what is the object to which we apply F equals ma. Okay, this could be the horse, this could be the wagon, or could be the horse and wagon together, because everything has the same acceleration. Wagon and the horse, and moving as one piece. Now, if you want to understand the motion of the horse, okay, then let us isolate the horse out as our system. When I say a system, I mean this is a particle or a collection of particles to which I'm applying Newton's second law. Okay, when I say I'm applying Newton's second law to this system, then what is the force about this system? Well, two things. There are forces exerted on the system, in other words, on the horse, and there are forces exerted by the horse or by the system. And when you apply Newton's second law, F equals ma, that F is only the force exerted on the system. In other words, on the horse, not by the horse. Let us be absolutely clear about that. Now, given that, we can easily understand why the horse always wins. Okay, remember, we only care about the force exerted on the horse, not the force given by the horse to somebody else. Okay, because we want to use the horse as our system, apply Newton's second law to the horse to understand its motion. All right, so who is exerting a force on the horse? Of course, the wagon, right? The wagon exerts a backward force. Okay, there's a backward force here. Okay, of course, there's another force here. So both forces try to pull the wagon backwards. If they were the only two forces exerted on the horse is going to accelerate backwards. There's no question about it. But don't forget, the horse is actually pushing on the ground as well. Okay, the horse is actually, you know how you go forward, right? You try to push the ground backwards. Okay, you try to push the ground backwards, and the ground, by reaction, will exert a force on you that is forward, right? That force has to be considered as well, because after all, that is a force exerted on our system, which is the horse. So, at least in the horizontal direction, okay, we know there are 3 forces exerted on the horse. There is this forward force from the road, and these are the 2 backward forces from the wagon. What determines the motion of the horse is the net sum of these 3 forces, forward minus the backward. And if the forward force is equal to the backward force, then the net force on the horse is 0, which means the horse can move forward with a constant velocity. And if the forward force exceeds the 2 backward forces, then the horse is actually going to accelerate forward. Okay? True, the horse also gives the wagon a force, but I don't care as far as the motion of the horse is concerned. That force only affects the motion of the wagon. It does not affect the motion of the horse. Okay? Because that's a force given by the system, which is the horse, not on it, not the force on the system. Okay? And remember, F equals ma, this F is only the force given on the system, exerted on the system, not by it. Now, what about the wagon? Well, if you understand the motion of the wagon, what we need to do is figure out the force exerted on the wagon by somebody else. Okay? So what are these 2 forces? What are the forces? Well, first of all, since the wagon is pulling the horse is also pulling the wagon here with the exact same force. Okay? Also, the wagon is pulling the horse from a different location, so the horse, with reaction, also pulls the wagon forward. Of course, the wagon also receives a little bit of friction from the road, which is against it, like this. But as long as these 2 forward forces exceed the backward force, then the wagon is going to accelerate forward. Okay, so that explains why the wagon accelerates forward. Now, why did we not consider these 2 forces when we try to understand the motion of the horse? Is because these 2 forces, again, are the forces exerted by the horse on somebody else, which is not the force the horse itself receives. So it has nothing to do with the horse itself, with the motion of the horse itself. We only consider these forces when we study the motion of the wagon, because those are the forces exerted by the horse on the wagon. Okay? Now finally, if we consider both the horse and the wagon as one grand system, like this, an entire system, what can we say? Well, this is one system now. Okay? I can do so because different positive systems have the same acceleration. Now, if we did so, we find what are the net forces? Well, let's add all the forces up. All these forces become relevant now because, these are all, forces exerted on certain positive system, right? So, we have this force forward, we have that force backward. And there are also 2 pairs of forces, one here, one here. But guess what? They cancel out, don't they? Because, action and reaction, right? According to Newton's 3rd law, this force cancels with that force, this force cancels with that force. So how come these forces cancel out and those don't? Okay, let's make an important distinction between these forces and those forces. These forces, look at this pair. Okay, this is the force given by the wagon to the horse. That is the one given by the horse to the wagon. Okay? And we add them both together and they cancel out. And this should come as no surprise because of action and reaction. Newton's 3rd law says that they have to cancel out. And how do we know immediately that we don't even have to consider these forces because they cancel out anyways? Because these are what's called internal forces. Okay, why are they internal? Because they are the force between one part of the system and another part of the system. Okay, between the wagon and the horse. Same thing here with this pair. So when a force is internal, which means it comes from one part of the system, it acts on another part of the system, we don't even have to bother studying it, because by action and reaction, every one of those forces must be accompanied by its reaction, which just cancels out if we add both of them together. So internal forces do not change the motion at all. What about this force? this force is from the road. Now, the road is not part of the system, which consists of only the horse and the wagon. And therefore, that is called an external force because it came from somebody else outside the system, which in this case is the horse and wagon. It came from the road, which is not part of the system. So is this friction. This is also from the road, which is not part of the system. Those are called external forces, and from this analysis we know only external forces should be accounted for. Okay, so therefore, from this study we conclude that when we apply F equals ma, this force F is the net external force. Okay, internal forces never matter because they just cancel out by Newton's third law.